This video is all about how to apply transformations to parent functions. We're going to take a function like y equals x squared and then be able to apply all these different transformations to it to get this new graph shown on the right. We'll begin by applying the transformations one at a time to the quadratic function, and once we've established what all the transformations do, we'll apply those transformations to absolute values, square root, and reciprocal functions. If you're looking for a specific type of function, you can see in the timestamps on the bottom of this video where those different functions are shown with transformations. So as we begin by considering the quadratic formula, y equals x squared, we apply the transformations a, k, d, and c to that squared function. And so let's look at what the a value does. The a value is a vertical stretch or compression by a factor of a. In other words, you're going to multiply the y values by the a value. Not the x values, but the y values, because that's the thing that is a vertical coordinate. If the a value is bigger than 1, it is a vertical stretch. And if the magnitude of the a value is between 0 and 1, then it is a vertical compression. Notice I said the word magnitude of a, because if the a value is negative, then that means it's flipped over the x-axis, or reflected over the x-axis. So we look at the number part of it, and then we look at the sign part of it to see if it's flipped over the x-axis. The k value is a horizontal stretch or compression by a factor of 1 over k. By horizontal stretch, we mean that the x value is being multiplied by this factor. That factor is the reciprocal of what the k value is. This is very important to remember that it's the reciprocal. It's 1 over k. So if the k value is between 0 and 1, if it's a fraction that's smaller than 1, then what that means, it is going to be a horizontal stretch because the factor is 1 over that. We'll look at those examples in a moment. If the k value is bigger than 1, then it's a horizontal compression. Now, before we look at the examples, I want to first point out the very clear distinction we need to make between vertical and horizontal. Make sure that you're applying the a value to the y coordinate and the k value to the x coordinate. Very important to remember. So now let's look at a couple of examples applying to the k value. If the k value is a half, that means that the factor is 1 over a half, and 1 divided by a half means that that's equal to 2. If the k value is 3, that is a horizontal compression by a factor of 1 over 3, the reciprocal of whatever we have as our k value. So now let's look at what happens if the k value is negative. And just like it is for the a value, it's going to flip it, but it's not going to flip it over the x-axis as it did for the a. It's going to flip it in a horizontal manner, which means it would flip it over that vertical axis. Flip it side to side over the vertical y-axis. The d value is a shift d units left or right. Now you'll notice up in the equation at the top it says x minus d. And so what that means is it's going to shift to the right if the d value is positive. We'll see an example here that would be a situation like if you have x minus 3. Because the d value, it's written as x minus d, so that means the d value would be positive 3. It would be shifted to the left if the d value is negative. So in other words, if you had something like x plus 4, that doesn't look negative, but remember if it's x minus d, if that's the form, then it's x minus negative 4. That's the same thing as x plus 4. So that would be a d value of negative 4. The c value is a shift c units up or down. And this is fairly intuitive, just as we would expect. If the c value is positive, it's going to shift it up. If the c value is negative, it's going to shift it down. So if we look at the a, k, and d and c values, a and c are probably fairly intuitive to you, but k and d seem a little opposite to what you would expect. We're going to dig into that as we look at some examples and the why behind that. So let's look at just a situation where we just have an a value. Notice this is not negative 2 and it's not being squared at all. And so because of that, it's just the a value. So the a value is negative 2. And what that means is it is, first off, it is flipped or reflected over the x-axis. Reflected over the x-axis. And then the fact that it is 2 means that it is going to be vertically stretched by a factor of 2. So vertically stretched by a factor of 2. By a factor of 2. And so let's see what that looks like on the graph here. So it's important to start off whenever we graph a quadratic. This is the quadratic y equals x squared. That we have these 5 key points for this particular parent function. We have the point 0, 0, 1, 1, negative 1, 1, 2, 4, and negative 2, 4. Because those are the points we're going to transform and then draw our curve through those points. So if we reflect this over the x-axis, that means that what I'm going to do is I'm going to take the first point on the left here, negative 2, 4, and I'm going to reflect it over the x-axis. So it's going to come here down to negative 2, negative 4. And then what I'm going to do with the point negative 1, 1, it's going to reflect over the x-axis again to become negative 1, negative 1. 0 stays at 0. There's no x-axis above that it has to flip over, so it's still on the x-axis. And then 1, 1 is going to reflect down to 1, negative 1, and 2, 4 is going to reflect down to 2 and negative 4. And so what we see there is not the full transformation yet. This is just the transformation y equals negative x squared. So the last thing we need to do here is we now need to apply the transformation that vertically stretches it by a factor of 2. So we're multiplying all the y values by 2. And so whatever I had on that last function, I'm going to multiply these by 2. So if I start at the far left point again, it is down at negative 4. If I multiply that by 2, it comes down to negative 8. If I multiply the next point, which is at negative 1, by 2, that becomes down to negative 2. 0 times 2 is still 0. I'm down here, negative 1 times 2 gives me negative 2. And then negative 4 times 2 gives me negative 8. And so now what I can do is I can draw my curve through all those points, and this is the curve y equals negative 2x squared. Now some of you might see a shortcut for this because really you can do all this in one step. What I could have done is flipping over the x-axis and vertically stretching it by a factor of 2 all at once by multiplying all the points by negative 2. In fact, all the y coordinates by negative 2. If you look at those y coordinates and you multiply each of those by negative 2, you get the points that are shown on the black curve. And so really that's all can be done in one step by simply multiplying everything by that a value. Now here's another situation where that number is associated with the x. So it's 1/2 times x all squared. Now that means that's the k value. So because the k is equal to 1/2, what that means is it is horizontally, and remember it's the factor of 1 over k, so it's horizontally stretched by a factor of 1 over 1/2. Well, what is 1 divided by 1/2? Well, 1 divided by 1/2 is just 2. So this factor is going to be 2. So what that means practically on the graph is we're going to take our key points on the parabola y equals x squared, and we're going to multiply all the x coordinates, because it's horizontal, we're going to multiply all the x coordinates by 2. So I take the x coordinate of 2 and I multiply that by 2, and that gets me out here to 4. So I'm at the point 4 and 4. Notice the y coordinate hasn't changed. This is all horizontal transformation. We're going to do the same thing with the next point, 1, 1. We double 1. The x coordinate is 1, so we double 1. That becomes 2. 0 times 2 is still 0. Negative 1 times 2 comes out here to negative 2. And then negative 2 times 2 comes out here to negative 4. And so what we're going to effectively get here when we draw our curve through these points is we're going to look and get a situation where we have this right here. And so this is the graph y equals 1/2 x all squared. Now I said earlier that I would address also why this is the case, because it kind of seems counterintuitive. Like, why is it not just 1/2? Well, here's what you need to think about. The reason this works is because what would you have to put, if I had the equation y equals x squared, what would I have to put to get 1 for y? Well, I'd have to put x equals 1, because if x equals 1, 1 squared would give me y equals 1. Well, what do I have to put in for x now with this 1/2 times x all squared in order for y to be 1? Well, I'd actually have to put in x equals 2. If I put in 2 for x, 1/2 times 2 would give me 1 squared, and that would give me y equals 1. And so because we have to put in a number for x that's twice as big as the original number I put in, that's why this is a horizontal stretch rather than a horizontal compression. For this next situation, we have a negative 2 in front of the x. And just like it was in that last example we looked at, that's the k value, because it's not added or subtracted to the x, it's multiplied by the x. And it's not outside of the brackets here, it's being applied to the square as well. So k is negative 2, which means that it is flipped over or reflected over the y-axis. So reflecting it over this y-axis, so flipping it like this. Now you can see here with symmetry, that's not going to do anything to the graph here, but in general, we'd flip them over like that. And it's also going to be a horizontal. In this case, it's a compression, because it's always the reciprocal of the number you see there. It's a horizontal compression by a factor of 1 over that number, 1 over 2. And so, in effect, what we're going to do is we're going to multiply all the x values by negative 1/2. The negative flipping over the y-axis, and the 1/2 horizontally compressing it by the factor of 1/2. So, if I took the point negative 2, 4 right there, what I'm doing is I'm flipping it over to there, and I'm multiplying it by 1/2, so it's going to come into there. And because of symmetry, it really just means that each of these just comes in by 1/2. So for the other side, 2, 4, flip it over, bring it in by 1/2. In other words, you were at 2 on the x, or negative 2, and it's going to come into 1 and negative 1. And so now we're going to look at the same thing with 1 and 1. That's going to flip over to negative 1, 1, come in by 1/2, so it's going to come to there. And then the point on the other side, negative 1, 1, it's going to flip over here and come in by 1/2 to there. And so what we can see is we have this skinnier parabola that has been horizontally compressed. And it's also been flipped over the y-axis, but we can't really tell that because of the symmetry. So before we put all this together, let's just have a look at the d and the c values here. This one is the case of the c value. So that is a number not associated with x. It's being subtracted from the x squared. And so what that means is the c value is negative 3. That means it is a vertical shift 3 units down. A vertical shift 3 units down. If it was plus 3, it would be a vertical shift 3 units up. And so we're going to take each of those coordinates, starting at negative 2, 4. We're going to shift it down 3. We're going to now go to negative 1, 1. We're going to shift that point down 3. We're going to go to the point 0, 0, shift it down 3. Go to the point 1, 1, shift it down 3, and the point 2, 4, shift it down 3. And so we're going to have the same shape. Nothing is being squished at all here. It's the same shape, but now this is y equals x squared minus 3 versus y equals x squared. That was 3 above for all those points. So before we put it all together, let's have a look at y equals x plus 3 all squared. Now notice that it is added to the x before it is squared. So what that means is that's the d value. Now, that's actually a d value of negative 3, because if you remember, our general form is a times k times x minus d all squared plus c. And so if it's a minus, it's actually positive, but if it's a plus, it means we're subtracting a negative. So in this case, it's d is negative 3. And what that means is we're going to shift 3 units left. 3 units left. So I'm going to take each of these points, and I'm going to shift them 3 units left. So if I start at negative 2, 4, shift it 3 units left. Negative 1, 1, shift it 3 units left. 0, 0, 3 units left. And so we're going to, again, have the same shape by shifting all these points 3 units left. Nothing's being squished or compressed or stretched or anything like that. Same shape, but now this is y equals x plus 3 all squared versus the original function y equals x squared. So why is that the case? Why does the sign seem to be opposite what we would expect? Well, let's consider, again, the original parent function, y equals x squared. If x is 0, 0 squared means that y is equal to 0. Well, how do we get y to be 0 in this new function, y equals x plus 3 all squared? Well, the only way to get y to be 0, to get that vertex, is if I substitute x equals negative 3. Because negative 3 plus 3 is 0. And so that's the only way we can get y to be 0 for the vertex of that one. And so it has to do with what we'd have to sub x in order to get that new vertex. And because we have to sub in an x value that's actually negative 3, that's why the sign of what is added or subtracted from the 3 is opposite what you would expect. Let's go ahead now and put all these together, the a, k, d, and c values with a quadratic function. So putting it all together, remember the general form is y equals a times k x minus d all squared plus c. And so what that means here is that the a value is negative 2. And so that's going to be a flip over the x-axis. That's the first thing. And then we also know it's going to be a vertical stretch by a factor of 2. And so what that effectively does is it is going to multiply the y values by -2. So we're going to take each of the y values and multiply them by -2. And so if I have a y value of 4, in this first case of -2, 4, multiplying that by -2 brings me down here to -8, keeping the x value the same. -1, -1, we take the y coordinate again, we multiply that by -2, that brings it down here. We take 0, 0, that's not going to change. -2 times 0 is still 0. -2 times the y value of 1 there is going to make it -2. And the -2 times that 4 is going to make that -8. And so we're going to have those points right there. And that now is just with the a value applied. So this graph here is y equals -2 times x squared. So now let's go ahead and apply the k value. The k value is 1/3. And so what that is it's always the reciprocal factor. So that means it's a horizontal stretch by a factor of 3. Horizontal stretch by a factor of 3. So what that's going to do to the graph is it's going to take all the x coordinates and multiply those by 3. So here I have an x coordinate down there of -2. I'm going to take that and multiply that by 3. That's going to give me -6. I have an x coordinate here of -1. I'm going to multiply that by 3. That's going to give me -3. And I'm going to do the same thing for all the other coordinates. Now when I do it to 0, that stays there. But then at +1 becomes 3. And the x coordinate of +2 becomes 6. Notice we're keeping all the y coordinates the same. The y coordinates were changed by the a value, not the k value, and it's the x coordinates that are changed by the k value, not the a value. So now my graph looks like this. So this becomes y equals -2 times 1/3 x all squared. The last thing we now need to do is apply the c and the d values. So in order to apply those, what we're going to do is we're going to recognize that the d value is actually -4. Remember that it's subtracting a negative if it says plus there. And so that's -4, which means it's going to shift 4 units to the left. And then the c value is 5, which means it's going to shift 5 units up. And we're going to apply those together because really shifting over and up is a pretty easy thing to do. So we're going to take each of these points and we're going to shift them 5 up and 4 left. So I'm going to take this point right here. I'm going to go 5 up. So 1, 2, 3, 4, 5, and over 4. I'm going to take the next point right there, that one. 5 up, and then over 4 to that point right there. The vertex was at 0, 0. It's going to go up 5 and over 4. So its new vertex is going to be at -4 and 5. I'm going to do the same thing with this next point here. 5 up, 4 over, right to there. And then 5 up with this next point, and 4 over, which should land me right there if I've done that properly. So now I'm going to draw a curve through all those points. And this is that fully transformed function. This right here in the black is y equals -2 times 1/3 x plus 4 all squared plus 5. And we fully transformed this function. So more generally, these transformations are written in the form y equals a times a function of kx minus d plus c. And so what we've just graphed is we've graphed the function f of x equals x squared. Now you'll notice everywhere we had the x, we replaced it with k times x minus d in the x squared function. So we replace it and we get y equals a, and where we had f of x is being replaced with f of kx minus d. So the function is x squared. So we're replacing the x with the kx minus d all squared. And then we add the c at the end. So the k and the d are things that are affecting the x value, and the a and the c are things that are affecting the y value. If we apply that to the absolute value function, it looks like this. The k and the x minus d is in place of the x that was in between the x absolute value functions, and then the a and the c are outside of that. If we look at the square root function, what we see for that one is a very similar thing, where we have a, then we have the square root of k times x minus d, and then the plus c is outside the square root. The reciprocal function is a little trickier because what we have here is a fraction. And so what we're going to do is we're going to have a first, and then we have 1 over x, but the x is replaced with k times x minus d again. And so it's written like that at first, where that kx minus d has replaced the x. But then we can also change that because a times 1 is just a. So we can write the a up in the numerator, and it looks like that. So we're going to use those transformations now to graph the absolute value, square root, and reciprocal functions for 3 different examples using these transformations. So here we see a square root function that has an a value, a k value, a d value, and a c value, like that general formula that I'm writing below. The parent function that we have for this is the square root function. Y is just equal to the square root of x. And so what we need to do is we need to now determine what the a, k, d, and c values are going to do. The a value is 3, which means it's going to be a vertical stretch by a factor of 3. We're going to multiply all the y values by 3. The k value is -2. That -2 is something we have to think about because it's the reciprocal of the magnitude of 2. So it's a horizontal, and we'll leave if it's a stretch of compression blank for now, but we know that it's by a factor of 1 over the k value, so 1 over 2. And so because I'm multiplying all the x values by a half, that means it's going to be a horizontal compression. So horizontal compression by a factor of a half. And the negative part of that means that it flips or reflects over the y-axis. So it's a horizontal transformation by flipping over the y-axis, and that's important to keep in mind. That's going to be able to flip it side to side about that y-axis. The d value is 1, and that means it's going to shift 1 unit to the right. Now notice the general form is x minus d, and so that's why the d value is +1 and going to the right. The c value is -4, which means it's going to shift 4 units down. And those are the transformations for that parent function. Let's now apply those to the graph. What we have on the right is we're going to start by graphing the parent function. The parent function has those key points. Whenever I put 1 in for the square root, I get 1. If I put 4 in for the square root, I get 2. When I put 9 in for the square root, I get 3. So that's how I generate those y values from those x values. And then what I do is I go and I apply the a value first. Now that vertical stretch by a factor of 3 means I'm going to multiply all the y values by 3. 0 times 3 is still 0, but 1 times 3 is 3. So that value, the second value there, is going to go up to 3. 2 times 3 is 6, so that's going to move up to 6. Notice we're keeping all the x values the same. And then 3 times 3 is 9. And so we draw our curve through those 4 points, and that's the line y equals 3 times the square root of x. Now we go ahead and apply the k value. Now it's a horizontal compression by a factor of a half, and it flips or reflects over the y-axis. So in essence, what we're doing is we're multiplying the x values by -1/2. But let's just see how that applies one piece at a time. So the horizontal compression by a factor of half says we're going to multiply the x values by a half and then flip it over the y-axis. So instead of being a half, it becomes -1/2. The next point was at an x value of 4. We multiply that by a half, it becomes 2, and then we flip that over the y-axis and it becomes -2. The final point is up at 9. We multiply that by a half, we get 4.5, and then we flip that over the y-axis and we get -4.5. And so the 0, the origin point, is still 0 because that times -1/2 is still 0. And so we can draw our curve between all 4 of those points, and that's the equation with both the a and the k value applied. Lastly, we're going to apply the d and the c value together. And so we're going to shift every point on the red graph 1 to the right and then 4 units down. And so that's going to give me the point 1, -4. And then I'm going to shift the next point 1 over and 4 down. And that's going to give me the point 0.5 and -1. And then I'm going to do the same thing with the other points. We're going to end up with the point -1, 2. And then the next point, which is going to give us -3.5 and 5. Then with those 4 points, we're going to draw our curve through them, making sure that we're still starting at that starting point, not going past it. And that is our fully transformed function with all the a, k, d, and c values applied. So let's consider the domain and range as well here. The domain is x is the set of all real numbers such that x is less than or equal to 1. The range is that y is a set of all real numbers such that y is greater than or equal to -4. And what you'll notice here is that the shift 1 right and the shift 4 down affect what the x and y values are in the domain and range. And so there you go. That is our final transformed graph. So in this question, we're applying transformations to the absolute value function. And what I'm doing here is I'm writing the general formula out of the absolute value function. Now you'll notice the a value is -4, the k value is 1/2. The d value, though, is a little bit tricky, because if it's x minus d, then we can rewrite the plus as x minus -3. So that means the d value is going to be -3, and then the c value is going to be 7. The parent function that we're graphing here, as we already mentioned, is y equals the absolute value of x. Let's go ahead now and list what these transformations are going to do to the graph. So first, the a value is -4. That is going to be a vertical stretch by a factor of 4. We're going to multiply all the y values by 4. The negative part of that makes it flip over the x-axis, or reflect, you could say, over the x-axis. And so we're really going to multiply all the y values of all the coordinate points that we can identify on the curve by -4, keeping the x values the same. The k value is 1/2. Now the thing about the k value is you always have to take the reciprocal. And so this is a horizontal stretch because the reciprocal is 1 over 1/2, or 2. So it's a horizontal stretch by a factor of 2. 1 divided by 1/2, which is 2. Now to the d value. We've already broken down that it's subtracting a negative. So what that means is that the d value is going to be -3. And so what that's going to do is it's going to shift the graph 3 units to the left. It's very important you get that right and that you always break down a plus into subtracting a negative so you don't make that mistake. The c value is just 7. It just reads right off the graph. If it's positive, it shifts up. If it's negative, it shifts down. So this is 7 units up. And they're the transformations for that function. Now let's go ahead and graph that. If we graph the parent function, it has all these points. I just substitute an x value of 1 in, I get 1. I substitute an x value of 2 and I get 2. But if I put negative x values in, they become positive y values. And so I just draw my line through those key points. That's the line y equals the absolute value of x. Now I'm going to apply the a value of -4. What that does is it multiplies all the y values by 4. So we're multiplying 1 times 4 gives me 4. But then I'm flipping it over the x-axis, and so it's coming down to -4. I do the same thing with 2. 2 times 4 gives me 8. I flip that over the x-axis. It gives me -8. And then I do the same thing. It's just symmetrical on the other side. 1 times 4 is 4. Bring it down to -4. And then the 2 comes down to -8. 0 stays at 0 because 0 times -4 stays at 0. And now we can draw our line between those 5 key points. And that is y equals -4 times the absolute value of x. Now we apply the k value of 1/2, which is going to horizontally stretch by a factor of 2. In other words, we're going to multiply all the x values by 2. So I look at my x value of 1, so at the point 1 and -4, and if I double the x value, that comes to 2. The next x value is at 2, I double that, it becomes to 4. And I do the same thing on the other side of the curve. By doubling those values, they're just the negative same values as on the right. And that's y equals -4 times the absolute value of 1/2 x. The last thing we're going to do now is apply the shift 3 units left and 7 units up. I'm going to do that starting at the point 0, 0, because that's the easiest one to do that with. I'm going to go 3 left, 7 up, and there's my max point of this particular graph. And so what I'm going to do now is I'm going to look at the pattern from that max point. So I went over 2 to the left and down 4. So then where that new max point is, it's going to go over 2 to the left and down 4. On the right side, I'm going to go over 2 to the right and down 4. And then from each of those points, I'm going to go over 2 and down 4 to keep the pattern of what we had on the red below. You could also take each of the points on the red line and you could shift them 3 left and 7 up, and they end up being the same points that I'm graphing right there. So now we draw a line between those points, and that is our fully transformed function. That is a function y equals -4 times the absolute value of 1/2 x plus 3, and the absolute value, and then plus 7. So now let's look at the domain and range. The domain is x is the set of all real numbers. And you'll notice that because it goes out forever on the left and forever on the right, there's no restrictions on the domain. The range, however, does have a restriction because it doesn't get any higher than 7. So the restriction on the range is y is a set of all real numbers still, but the restriction is that y has to be less than or equal to +7. Now you'll notice for this particular situation, shifting 7 units up has actually affected the range, but there's nothing about the 3 and it's left that affects the domain, and that's because the domain is the set of all real numbers, and that doesn't change by shifting it left or right. So this question says, list the transformations of the function shown. Now that's the parent function of a 1 over x function. So it's a over k times x minus d plus c. That's what the variables are that we're going to look at as far as transformations. As I already noted, this is the 1 over x function, otherwise known as the reciprocal function. So y equals 1 over x. And so let's look at what the a value is and what it's going to do to the function. The a value is 3, which means it's going to do a vertical stretch by a factor of 3. We're going to multiply the y values by 3. It's literally that simple. Don't change the x values, but multiply the y values by 3. The k value is negative a half. And what that's going to do is it's going to do a horizontal stretch, because the ratio we're looking at is always the reciprocal of the k value. So the reciprocal of 1 over 2 is 2. So that's a horizontal stretch by a factor of 2. But the negative means that it's going to be flipped or reflected over the y-axis, right? The k value reflects or flips over the y-axis, the vertical axis. So it goes side to side. Last but not least, we have the d and the c values. The d value, because the general form is x minus d, is positive 4, which means it's going to shift 4 units to the right. And then the c value is going to be 6, which means it's going to shift 6 units up. And those are all your transformations that we would apply to that reciprocal function. So now we go ahead and move to the graph. If we go to graph this, we're going to start by graphing the reciprocal function. And the key points we want to do is 1, 1, 2, 1/2, and 1/2, 2. And then we draw our curve through those 3 points. And then we do the same thing in quadrant 3, but now with the x values and y values being negative. And we're going to draw a curve through those 3 key points. That is the function y equals 1 over x. Now we're going to apply the a value of 3, which means we're going to multiply the y values by 3. So looking at the first key point there, where I'm at a y value of 2, multiply 2 by 3, we get 6. Notice the x value still is 1/2. We look at the next key point, 1 times 3 is 3, x value is still 1. The y value, 1/2, goes to 3 over 2, x value is still 2 there. And so now we draw our curve through those 3 points, and that's half of the new transformed function. We do the same thing down in the quadrant 3. And so negative 1/2 becomes negative 3 over 2, negative 1 becomes negative 3, and then the y value of negative 2 becomes negative 6. All the x values staying the same. And so we now draw our curve through those 3 points, and that is the fully transformed graph of y equals 3 over x. Now we go ahead and look at the k value. So because we want to horizontally stretch it by a factor of 2 and flip it over the y-axis, it's really just multiplying all the x values by negative 2. The first point we're going to look at here is the point 2 and 1.5. And so the 2 is the x value. We multiply that by 2, we get 4, and then we flip it over the y-axis to get negative 4. We do the same thing with every subsequent point along the curve, doubling the x value and then flipping it over the y-axis, and we get it to move to quadrant 2 from quadrant 1. And so there is our half of the transform function. And now we do the same thing in the bottom left quadrant. So we're doubling all the x values without changing the y values, and then flipping them over the y-axis. And so you can see that that first point becomes 4, negative 1.5. Next point becomes 2, negative 3. And the final point there becomes 1, negative 6. And so we draw our curve through those 3 points, and that is the other side of the hyperbola, the other side of the reciprocal function. And so this is with the a and the k value applied. So this is 3 over negative 1/2 x. Finally, what we're going to do is we're going to transform it with the d and the c values together. Now, a really key thing to notice here is that the original asymptotes that we had on the green function drawn there is we had one at x equals 0 and we had another asymptote at y equals 0 on the actual x and y axes. And so what the shift left and right are going to do is it's going to move the asymptote. So the asymptote is going to shift 4 to the right, which means it's going to be at x equals 4. And then the other asymptote is going to shift up 6. So that means the asymptote is going to be at y equals 6. So while that principle of shifting all the red points right 4 and up 6 still applies, we can actually instead look at how far they are from the original asymptotes. It's over 2 and down 3 to one of those points. And so I can move that point over 2 and down through 3 from where those asymptotes now meet. And so I'm going to do that same thing with another point. I'm going to go over 4 and down 1.5 from where the asymptotes meet. And then that last point that was -1, -6, that's going to be 1 over and down 6 from where the asymptotes meet. And so I'm going to do that same pattern to plot that point as well. And so now I have 3 points. That's half the hyperbola now drawn. And so I have that half in quadrant number 2. Now, as we go into the next quadrant for the other half of the hyperbola, we do the same pattern. We look at how far I was from where the asymptotes met, going over and up or up and over. It doesn't matter how you look at that, just so long as you keep that pattern consistent. So here I'm going up and then over, using that same pattern, same distance with both the x and y from the point at which those two asymptotes meet. Notice that last point doesn't fit when I transform that, so I've just drawn it with those 2 points. Altogether, this is the curve y equals 3 over -1/2 x minus 4 plus 6. And that is your fully transformed function. Last but not least, let's look at the domain and range. The domain here is x is a set of all real numbers, but then it has this restriction at the asymptote. X cannot be 4. The range is y is a set of all real numbers, such that y cannot be 6, because it has the restriction at that asymptote. But otherwise, it's every other x and y value. And so those correspond really nicely to the d and c values, but they don't do that always for all the parent functions, but they do for this particular parent function. Having seen it on a graph, let's now look at what happens to the individual coordinates of x and y as we apply those transformations. The k and the d values affect the x coordinate, and the a and the c values affect the y coordinate. And so if we apply the a value first to our point xy, what we end up doing is we multiply the y value by the a value. And so that just changes the y coordinate and makes it, the x value stays the same, but we have a times the y value. If we go ahead now and we apply the k value is always multiplied by 1 over k times the x value. And so we get the x value being multiplied by that, and then the y value still being multiplied by a. Now if I apply the d and the c value here at the end, what I find is that the d value is added to the x value that's already been multiplied by 1 over k, so 1 over kx plus d. And the c value is being added to the y value. It's already been multiplied by a, so ay plus c. So if you start with a point x and y, any point, any coordinates, if you multiply the x coordinate by 1 over the k value and add d, and you multiply the y value by a and add c, that is going to be your final transformed point on the transformed function. And so that's kind of a shortcut way to check that, or just an alternative way to do that if you want to do that or you're asked to do that in that way. If you want more information about how to apply transformations to exponential functions, check out the video on the left. For more about applying transformations to sinusoidal functions, check out the video on the right. Thanks so much for watching, and I hope that was helpful.